So inshallah today we'll continue, and inshallah by the end of last 15 or 20 minutes, inshallah we'll convert to the presentation, the first presentation by I think Hassan.
Yes, doctor. Yes.
So inshallah today will be last 15 to 20 minutes. Yani just شباب, the idea is just yani to search a topic, try to know yourself about this topic, and then actually all of us will benefit just hearing actually to what you are presenting here. So yani we cannot cover all topics, but yani at least we can add to what we are doing actually in this course. طيب but the idea شباب يعني in overall we don't need you يعني to come with something very significant. Just the idea is to read and present. يعني but we can, if we are able actually to make it يعني better presentation, so that actually the benefit will be bigger in this case. But actually we are not under any kind of pressure regarding those presentation. Inshallah, either you will get the full mark 5%, or you will be actually, if your presentation is a good one, so inshallah you may have additional bonus in this case. طيب, in the preceding chapter شباب, we have learned actually about the different kind of fuels, the fuel families, and how we can convert the name of the fuel. We know actually about the chemical structure of this fuel. And then we talk about the properties of fuel, and we have learned also how to write down the combustion equation for any kind of fuel. And even if we have the gas concentration using a gas analyzer from the exhaust gas concentration, even knowing the exhaust gas concentration, we are able actually to know about the air to fuel ratio, and also we are able to calculate the equivalence ratio, which is equal to 1 over the excess air factor, which is actually a very important parameter regarding actually the control of the operation actually of any combustion engine. Either we are talking about internal combustion engines, or we are talking about actually gas turbine, or any actually combustion system. We control actually the flame based on actually what's called the equivalence ratio, and this equivalence ratio should be actually within the operability limit of this actually kind of fuel. So each fuel has actually operability limit. This operability limit actually is dependent on a range actually, or it is existing actually in a range of operating equivalence ratio. So we have to be able to calculate the combustion equation for any kind of fuel. We are able to calculate the air to fuel ratio. Air to fuel ratio actual. If we are able also to calculate the theoretical air to fuel ratio, then we can calculate the equivalence ratio, which is actually the difference or actually the ratio between both of them. طيب, today inshallah شباب, in this chapter inshallah we'll learn how from this combustion equation, how we can apply actually the first law of thermodynamic for a reacting system like internal combustion engine or gas turbine, in order to calculate actually the heat of this combustion. We are able to write down the combustion equation to convert the reactant into product, but actually we need to calculate the heat of combustion, the amount of heat generated. And also using the first law of thermodynamic, we can calculate the work generated in the engine. Either we are talking about internal combustion engine, so the heat generated from the combustion chamber will just press on the piston, so the piston will be moved. When we have a movement, we apply force and get a movement. That means in this case we have work. Type, we need to calculate this work also of the engine. So inshallah, all of this will be through the first law of thermodynamic. We can apply the first law of thermodynamic to calculate the heat transfer of the combustion process, and also to calculate actually the power of the engine in this case. Either we are talking about internal combustion engine, or actually the second main application, which is the gas turbine. In the gas turbine, we take the exhaust gases and we pass them actually through the turbine. Turbine actually is a series of blades on an impeller, so the exhaust gases are leaving with high velocity jet, high pressure, high temperature. So it hit actually the blade of the turbine, then we can generate shaft power in this case. So also we can apply the first law of thermodynamic for a gas turbine system to calculate the heat transfer in the combustion chamber, and also we can calculate the power output of this turbine. طيب, inshallah, in this chapter, this is our target in this chapter 4. We'll talk about the chemical energy in relation to the static energy, how to write to get it actually from a combustion equation. I will give you a brief about closed system or open system, because Shabab, we have two kinds of combustion. Either we are opening, either we are doing combustion actually in an open system. Open systems, that mean we have mass flow rate in, mass flow rate out, that like the case of internal combustion engine or gas turbine. We call it open system combustion system. We have another kind of system, Shabab, in which we call closed system combustion. If we have combustion gases like inside a room or something, we call it, Shabab, in most of the cases it is a kind of explosion. So if we have fuel plus air in a constant volume combustion, closed system, we don't have mass in, we don't have mass out, and in this case we ignite inside this system, so we'll have actually in this case what we call actually a closed system combustion, or we call it constant volume combustion. It's a kind actually, Shabab, of explosion, like if we have a fuel tank and we just ignite it inside, so the fuel tank will just explode. So inshallah we'll be talking about also this case. So that's why I will be talking about open system and the closed system. Then I will be talking about enthalpy of formation, the enthalpy of combustion, how to calculate actually the heat transfer. The heat transfer, Shabab, due to combustion appear actually as increase in temperature and the pressure of the combustion product. Increasing pressure and temperature, that means we have higher enthalpy. So that's why when we calculate the heat transfer of combustion, we calculate it in terms actually of a change of the enthalpy between the product and the reactant. Inshallah, we'll learn this and we'll apply the first law of thermodynamic for open system like gas turbine or internal combustion engines. They are open. We have air plus fuel coming in and we have exhaust leaving. That means this is an open system. And we'll talk also about the combustion for a closed system, like when we have a bomb calorimeter or something. Then in this case, we will see how we can calculate the heat transfer in this case. We'll be talking about the heating value or the calorific value of the fuel, how we can calculate the heating value or the calorific value of the fuel, how to calculate the maximum combustion temperature. We call it the adiabatic flame temperature, which is the maximum temperature of a combustion, of a given combustion at a given condition. So inshallah, we'll learn how to calculate it for constant pressure combustion. Usually this is the open system, and for constant volume combustion, which is the case when we have a closed, or most probably we have a closed system in case of constant volume combustion. And we'll give you an indication about the combustion efficiency of some some devices. But before I go with this, I will just, is that clear, Shabab? For this chapter, what we are going to do? Hopefully there is no delay, yeah?
Yes.
So I just tried to connect the connection directly, the wire connection internet instead of Wi-Fi. So hopefully, inshallah, the problem will be solved, inshallah. We said we can apply the combustion either for a closed system or open system. So the different kind of system, we have either closed system or actually the system, we call it actually open system. Closed system, Shabab, is defined actually as a fixed amount of mass that has been selected to do a certain study. So by definition, the mass of a closed system is constant. That means, Shabab, if we differentiate, then we can say the mass flow rate, the differentiation of a constant will be 0 in this case. That means the mass flow rate will equal to 0, or mass flow rate inlet to the system or leaving the system is equal to 0. And this is, Shabab, the case of a closed system. We don't have either mass in or we don't have actually mass out. Just it is fixed amount of mass. But actually this system allow actually for energy transfer in both directions. We may have energy in, we may have energy out in this case. So what are the forms, Shabab, of energy transfer? I think you are all about this. Energy can transfer by heat in case if we have temperature difference delta T. Then energy can transfer by heat between any two systems of different temperature. Energy also can transfer by work if we apply a force and we get a movement distance L. That means we have a work in this case. Like the case, Shabab, of internal combustion engine, we have a piston, we apply a force due to combustion, the piston will be moving in this case. So in this case, we can get work out of this engine. And also, Shabab, energy can transfer by mass transfer. So if we have flow inside a tube or something, then in this case, this flow should have energy. We call it the energy transfer by mass in this case, like kinetic energy, potential energy, internal energy, the energy also due to the pressure, which we call it the flow energy. All of this energy, we sum them up actually in terms of energy transfer by mass. But in case of a closed system, we don't have mass transfer. So that means this term, energy transfer by mass, should equal to what, should equal to 0. And in case of closed system, energy can transfer by heat and the energy can transfer by work. Unlike the case of open system, we call it actually control volume. In this case actually of closed system, we call it actually control mass. Control mass, that means the mass is constant. But in case of open system, it is called the control volume, or actually in this case the volume will be constant. And it is defined as an arbitrary region, just any imaginary region, selected to do actually a certain study in a given space. So this boundary is just imaginary. We call it the control surface. Control surface, which is the surface of the control volume, and this is the control volume in this case. And as it is imaginary, so we don't have in this case any boundary. So that means in this case, mass can transfer. We may have a mass in or mass out of the system, and also energy in this case can transfer. We may have actually energy in or energy out. But in this case, energy can transfer in the form of heat, can transfer in the form of work, and it can transfer due to mass transfer. Because in this case, we have actually mass can come in and the mass can be leaving out in this case. If you look, if we have any tube like this, and we have flow inside this tube. So let's say we have a tube, and we have a flow inside this tube. So this flow, in order to move, let's say, from one location to another location inside this tube. So let's calculate actually the energy transfer by mass. This fluid, should be at a given temperature. That means it should have internal energy U. Okay? Type this flow, in order to move from this location to another location, should be pressurized. It should be under high pressure. Flow, cannot move unless there is a difference in pressure. Okay? Type this pressure, acts like a piston. So it applies actually the pressure force is applied here to move the fluid. The pressure is equal to the force divided by area. Right, we can say in this case the force will equal to the pressure by area. And the fluid will be moving from one location to another, let's say certain distance L. So the work in this case will equal to the pressure multiplied by A, which is the force, multiplied by L. Area multiplied by the distance, which is actually representing the volume. So the work in this case will equal to the pressure multiplied by volume. We call it, in this case, the flow energy. Flow energy is equal to the pressure, which is due to the pressure of the fluid, which acts like a piston in order to push actually the fluid. So the pressure force will equal to pressure by area. It will move the fluid a certain distance L. That means actually it will equal to the work in this case, to the flow energy is equal to the pressure multiplied by the volume. So the flow, in order to move, it should have actually a flow energy, which is equal to the pressure multiplied by the volume, plus the kinetic energy, plus the potential energy in this case. Kinetic energy, which is half mv squared, which is related to the velocity of this fluid, it should have kinetic energy. And this pipe, it should be actually given at a reference state to maybe the sea level or something, so it should have a kind of potential energy in this case. So if we have fluid at higher level, so that means actually this fluid should have higher potential energy in this case. Like the idea, of hydraulic dam. We have a water at high level, then we can just take this high potential energy of the water, which is part of energy transfer by mass. We can actually convert it actually into shaft bars through the hydraulic turbine at the bottom level actually of the dam in this case. So the energy transfer by mass is equal to the internal energy plus flow energy plus kinetic energy plus potential energy. Internal energy plus flow energy, we call it the enthalpy, H. So the enthalpy, is just the summation of internal energy plus the flow energy. But if we are talking about a combustion system, so usually due to combustion, temperature increase and the pressure actually will increase. So temperature will appear actually in this term, internal energy, and the pressure will appear in this term, flow energy. And both of them can be combined in terms of the enthalpy. But actually, the kinetic energy and the potential energy in this case can be neglected. And that's why the energy transfer by mass for a reacting system can be just reduced actually to the enthalpy of this flame. So in case of open system, like internal combustion engine or gas turbine, in this case, energy can transfer by heat due to combustion, energy can transfer by work due to actually the piston movement, you can generate work, and also due to burning the fuel, in this case, the enthalpy will be changed in this case between the reactant to the product. And this is the main difference between open system and the closed system. There is a special case when we have an adiabatic system. What does it mean adiabatic system? Adiabatic means what شباب?
It means no heat around.
Exactly. So in this case, if I say that adiabatic system, isolated, insulated system, that means the heat transfer should equal to 0. And we have a special case also when we say isolated system. If I told you in any problem we have isolated system, isolated or insulated, that means in this case the system does not allow actually for any kind of transfer, either mass transfer or energy transfer. So in this case the heat transfer is equal to 0, work out of the system is equal to 0, and in this case mass in or mass out is equal to 0. Just a fully insulated system, like when we just seal a system from the surrounding medium, we don't have any change, either work or heat transfer. But usually the isolated system may contain actually some internal subsystem that may exchange actually heat and energy, mass and energy between each other in this case. So it depends, if we are considering the whole isolated system, in this case actually nothing to study. Everything actually is equal to 0. But if we are studying one of the subsystems here, then we can just draw a control volume. And then we can look at actually the masses and the energy transfer in this case, and we can apply the first law of thermodynamic as we will be learning inshallah today. Is it clear, Shabab? Is that clear?
Yeah. Yes, clear.
Let's move to the first law of thermodynamic itself. Let's define the first law of thermodynamic in this case. So as I told you, Shabab, in case of a reacting system, we have high temperature rise due to combustion and high pressure, and this appears actually in terms of enthalpy of the product in this case. The enthalpy of the product will be increased in this case. But usually in the combustion system, Shabab, we neglect the change in kinetic energy and the potential energy, as actually their values are very low actually compared to actually the value of the enthalpy in this case. So let's apply the first law of thermodynamic for a reacting system. If we have actually any reacting system like internal combustion engine or gas turbine, so let's say here we have actually any reacting system, like if we have internal combustion engine or if we have gas turbine engine in this case, all of these actually are considered as our open system, open reacting system. So let's apply the first law of thermodynamics first of all. If we have a steady flow, open system. So we are considering the case of open system, like if we have internal combustion engine or gas turbine in this case. In this case, Shabab, for the system, if we have a reacting system, we should have actually fuel is supplied to this system plus air. This fuel plus air will be just burned inside the combustion chamber here inside this system, and some heat will be generated inside the system, like the internal combustion engine. Just inject the fuel plus air, so in this case actually heat will be generated inside. This heat will push what? Will push the piston to move. If the piston is moved, that means in this case the system is generating work. And at the end actually out of this system, we should have actually the exhaust gases or the combustion product. In case of internal combustion engine, we may have some heat is lost, like actually the heat losses to the cooling water system or the heat losses in the lubrication system, like this in the case of gas turbine. So usually we burn fuel plus air inside the combustion chamber. Some heat will be generated inside the engine. This heat can be converted to work, and the part of this heat due to combustion can be actually lost out of this system, maybe to the cooling system or something, and then we should have actually the combustion product at the end in this case. But as the system is open, so that means we have mass transfer in this case. So let's consider the mass equation. So based on actually on the law of mass action, so in this case, mass cannot be created or destroyed. So we have mass into the system minus mass out of the system. So equal to the part of mass remaining within the system itself. So mass in يا شباب should equal to mass out plus if we have some mass just still inside, remained inside, which we call it actually the change of mass inside the system itself. This is the mass coming in, mass leaving. The mass actually change inside the system in this case. But let's consider the rate form. So we can say rate of mass flow rate in minus rate of mass flow rate out will equal to the rate of
دكتور
Yes.
صوتك قطع فجأة.
الصوت في مشكلة في الصوت؟
لا بس الآن طالع. الآن تمام.
الحين تمام دكتور.
Okay. طيب what does it mean steady flow يا شباب? So this term should equal to what?
Zero. There's no change in the inside the rate.
So this term should equal to?
Zero.
Should equal to exactly zero in this case. Steady flow means actually we don't have a change of time, and in this case يا شباب, that's why we have the mass flow rate in. The mass flow rate coming in will be the mass flow rate actually leaving in this case. We don't have any mass accumulation inside the system. So in this case, the mass flow rate in, we have fuel plus air. So that means we have m dot air plus m dot fuel. That should equal to actually the mass flow rate actually of the exhaust gases. And this is a shabab what we call the mass equation in this case. Like this also shabab, we said mass cannot be created or destroyed. Also energy cannot be created or destroyed. Energy can be just transferred from one form to another form. So we can apply in this case the energy equation. So the energy equation, which is the first law of thermodynamic actually for a reacting system. The same way we can say energy in minus energy out will equal to the change of energy within the system. Or we can consider the rate form, rate of energy in minus rate of energy out will equal to the rate of change of energy inside the system. And this term should equal to zero if we are talking about a steady flow. So that means actually the rate of energy in should equal to the rate of energy out because this term is equal to zero. But in case of open system, energy in or energy out, energy can transfer by heat. So we may have heat in minus heat out, Q dot in minus Q dot out. But also energy can transfer by work. So we can say work dot in minus work dot out. Okay, and also in case of open system, we have mass transfer. We have energy transfer due to mass in minus energy transfer, rate of energy transfer by mass leaving the system. Okay. Or we can combine this about Q in and the Q out. We can just say actually this is Q dot. Either it is added or rejected. So we will be looking actually at the system. If the system have heat added, so we can consider it. If it is rejected, so it will be actually of different sign in this case. If we have actually both of them, then we can just add them up to have it actually the heat transfer in this case. So this can be just reduced to heat transfer, and work out and work in, we can just reduce it actually to in general to work. But usually the sign of the heat transfer is the opposite to the sign of the work. So usually if the heat is added, its sign is positive, and if it is rejected leaving the system, its sign should be negative in this case. So the heat transfer and work are directional quantities. So actually its amount, it depends on the direction. So if heat is added to the system, So that means its sign should be positive. If it is leaving the system, rejected, its sign should be negative. And the opposite actually is the case of work. And that's why we should have the negative sign in this case, because actually what we care from the system, we care actually about the work out of the system. Okay, we add heat and we get actually work out in this case. So actually heat is added in the direction actually of coming into the system, and the work out actually is leaving the system, so they have opposite sign in this case. So we can say Q dot minus work dot. We can take this term energy transfer by mass to the other side, so it will equal to rate of energy transfer by mass out minus rate of energy transfer by mass in. And we said in case of reacting combustion system, the energy transfer by mass can just be expressed actually by the change of the enthalpy, should equal to enthalpy plus kinetic energy plus the potential energy, but we neglect the kinetic and the potential energy, so the term of energy transfer by mass can be just reduced actually to the enthalpy. The enthalpy out minus the enthalpy in, which is the difference in enthalpy between the combustion product and the enthalpy of the reactor. And based on that, we can just write down the first law of thermodynamic will be Q dot minus work dot. The rate of energy transfer by mass will equal to M dot multiplied by the difference in enthalpy, which will equal to M dot multiplied by the difference between enthalpy of the product minus the enthalpy of the reactant in this case. Okay, is that clear, Shabab?
Clear, Victor. Yeah.
So in this case, if we divide this equation, Shabab, by M dot, so I will be just dividing both sides actually by M dot in this case. That means we can get here the specific heat transfer Q small minus a specific work that should equal to actually H product actually minus H reactant. And actually the unit in this case of all terms in this equation if you have are in kilojoule per kilogram. So the heat transfer to the system minus the work of this system should equal to the difference in enthalpy of the product minus the enthalpy of the reactant in this case. But usually, Shabab, when we write down the combustion equation, we write it actually for 1 kilomole of the fuel. So our calculation is based actually on 1 kilomole of this fuel. But let's multiply this equation by the molecular weight of the fuel in this case. Molecular weight is calculated in kilogram per kilomole. Multiplied actually by kilojoule per kilogram. That means in this case we can get the equation in terms of what if we multiplied by the molecular weight. So in this case we can get it actually in kilojoule per kilomole in this case. And in this case we can just write down the combustion equation per 1 kilomole of the fuel. So it will be Q bar minus 4 bar. This bar, ya shabab, indicate actually that it's the heat transfer or the energy transfer per kilomole of the fuel. So it will be Q minus work will equal to the difference in enthalpy H product minus H reactant. And the unit in this case of all term actually is in kilojoule per kilomole. And this is the first law of thermodynamic, shabab. For a reacting system, the heat transfer in kilojoule per kilomole minus the work in kilojoule per kilomole should equal to the difference in enthalpy between the product and the reactant in this case. Okay, but as I told you, Shabab, this heat transfer and work, they are directional quantities. So is their sign actually when it comes to substitute inside this first law equation, we have to substitute actually by its sign. So if heat is added to the system, so in this case actually its sign should be a positive sign. Like if we have a Shabab endothermic reaction, a reacting system. But those are endothermic reaction, like let's say the reforming of methane or something. So in this case, we have to add heat to the system. So in this case, when it comes to substitute to the first law of thermodynamics, this heat actually, if it is added, it should have positive sign. Or this heat actually may be rejected from the system or lost from the system. Like in case of internal combustion engine, some of the heat will be just lost to the cooling water. So in this case, actually, its sign should be negative in this case. But if the system is adiabatic, that means actually in this case the heat transfer should equal to 0. So heat in the first law equation, Q Q minus work equal to delta H. If it is added, like the case of endothermic reaction, it should be positive. If we are talking about internal combustion engine or gas turbine, in this situation, we may have some heat is rejected to the cooling water system. So if heat is rejected from the system, its sign should be substituted here by a negative sign. And if the system is adiabatic, the heat transfer will equal to 0. And the opposite is the case of work. If the work actually is produced from the system, like the case if we have internal combustion engine, gas turbine, those are work-producing devices. So in this case, the sign of the work should be positive in this case. Or it can be negative in case actually of work-consuming device, like if we have a compressor. In case of gas turbine, if you look to the gas turbine, there is a compressor connected in the sham shaft actually to the turbine, and between the compressor and turbine, we have the combustion chamber in this case. So the compressor compresses the air, then it comes to the combustion chamber to be burned with the fuel. We have exhaust gases under high temperature, high pressure. It can expand inside the turbine. If we are studying, in this case, the combustion chamber plus the turbine, I will draw a control volume around it, and I will say actually this is the space I'm going to study. But in this case, if you look at the turbine, in this case, there is a shaft here to drive the compressor. So in this case, we have to consider the work of the compressor in this case. While writing the combustion equation, the First Law equation, it will be Q minus work equal to H product minus H react. But which kind of work we do have in this case? If we are studying compressor plus turbine, the whole system, then in this case I have to add the compressor work. Because the compressor is taking part of the turbine work. And we have also the turbine shaft part. So we have the turbine work in this case. So in some cases, if I'm considering studying the whole system of the turbine, including the compressor itself, that means in this case I have to consider the compressor work. And the compressor work, is added to the system. We apply work to drive the compressor. Compressor is consuming work, turbine is producing work in this case. So if I'm considering the compressor, I should consider the work of the compressor, but it should be of negative sign in this case. But what if we are just only studying the combustion chamber? If I'm not studying the whole engine, like in case of gas turbine here, I'm just actually studying this combustion chamber. So I will just draw a control volume about this combustion chamber. Do we have any kind of work in this case, If I'm studying a combustion chamber or furnace in this case, I'm not caring about the turbine in this case. So do we have any kind of work?
No, only heat.
No, so only in the combustion chamber, we add fuel plus air, then we can generate heat. Then we can have heat transfer in this case. But actually this heat will be transferred to the combustion product. We'll have combustion product at high pressure and high temperature. But still, we did not use actually those combustion product in order to convert them to work. So if I am studying a combustor, or if we have a furnace or something, that means in this case we are just studying the combustion chamber in this case. We are not taking care about the work in this case. And in this case, the work should be considered as 0 in the First Law of Thermodynamic equation. Okay? So work can be positive if I'm studying the whole internal combustion engine or the whole gas turbine system. Can be negative if we have a device that consumes work in the system, and work can be considered in this equation as 0 if I'm only studying the combustion chamber or the furnace in this case. Is it clear, Shabab? Is it clear?
Clear.
Right. Let's see, Shabab, those terms, how we can calculate the enthalpy of product and the enthalpy of the reactant. So usually, Shabab, if I need to calculate the enthalpy, we don't have in thermodynamic a relation that can give us actually the enthalpy at a given temperature and a given pressure. So usually we have the relations that can give us actually the difference, delta H. For ideal gas, we can consider actually delta H is equal to Cv multiplied by delta T. So we have a relation that gives us the difference in reference actually to a reference point. But we don't have a relation that can give us actually the value of the enthalpy at a given pressure and a given temperature. And that's why we have to have a reference point in this case. Usually the reference point for, if you look at actually the steam table or any table, thermodynamic table, usually you will find this reference temperature is about actually 0 Kelvin. And based on the third law of thermodynamic, the entropy is assigned a value of 0 when we have actually the temperature is equal to 0 Kelvin. And based on this reference temperature, شباب, we have also assigned the enthalpy is equal to 0, and most probably, and also the internal energy is equal to 0 at this reference point, which is 0 Kelvin. But usually when we talk about combustion, شباب, we take the reference point, temperature is equal to 25 degrees C, and the pressure, which is atmospheric pressure, which is 100 kilopascal or 0.1 megapascal in this case, which are the standard atmospheric condition. Because the idea of the combustion, شباب, is to do what? Is to get heat of this combustion. But if we have a reaction at low temperature and it results in an amount of heat that is actually equal to the atmospheric condition. So will you feel this heat in this case? Will you feel actually there is a combustion or something? We are living in the atmospheric condition. So if we have a reaction that is being done at lower temperature than the atmospheric temperature, which is 25, so actually we cannot feel the heat transfer. We cannot feel actually the effect of combustion in this case. So in this case, for combustion, we consider the reference point to calculate the change of enthalpy is actually the standard atmospheric condition, which is temperature equal to 25, and actually pressure is equal to 1 megapascal. And in this case, delta H will equal to the enthalpy at a given temperature minus the enthalpy actually at the reference temperature, which is 25, which is the 25 degrees C in this case. And in this case, if delta H, if the temperature, we are doing a combustion system at a temperature equal to 25, that means in this case, delta H will equal to 0. If the temperature of the reacting system or the combustion system is greater than 25, that means delta H in this case will be a positive value in this case. And if the temperature is less than 25 degrees C, that means in this case delta H will be negative in this case. And based on that, we can just calculate enthalpy of product minus the enthalpy of reactant. This term, we can calculate enthalpy of product on the enthalpy of the reactant per kilomole of the fuel. That should equal to the summation for number of moles from equal to 1 to the total number of moles actually for each reactant or the product, each species in the product or the reactant, multiplied by the enthalpy of formation plus delta H. Enthalpy of formation, this is the enthalpy of formation, which is the required amount actually of heat or the heat generated in order to actually form a compound from its basic element. So let's say I need to have a compound like carbon dioxide from its basic element, which is carbon plus oxygen, under temperature equal to 25 degrees C and atmospheric pressure equal to 1 megapascal. If we perform this reaction of carbon plus oxygen, the basic element, in order to formulate actually carbon dioxide, this reaction is exothermic. So in this case, some heat will be generated due to actually this reaction. This heat, we call it what? We call it the enthalpy of formation of carbon dioxide. So the enthalpy of formation is the amount of heat created or needed in order to create actually an element or a compound from actually its basic element at the reference condition, temperature equal to 25 degrees C and the pressure equal to 0.1 megapascal in this case. And in this case, the enthalpy of the product or the reactant will equal to what? The enthalpy at the reference point, which we call it the enthalpy of formation. This value we can get from the table. Plus delta H. Delta H is the enthalpy at a given temperature that we want to calculate the enthalpy at, minus the enthalpy at the reference temperature. So enthalpy at the reference temperature, which is what? The enthalpy of formation. So that's why it is equal to the number of moles multiplied by enthalpy of formation plus the enthalpy at the required temperature, which we need, minus the enthalpy of formation again. So it will be enthalpy of formation plus H minus enthalpy of formation. So it will result actually in H in this case, which is the enthalpy that we want to calculate. But why we do it this way? Because, as I said to you, for the combustion, we have to calculate the properties in reference to a reference point, because we don't have a relation that give us actually the enthalpy directly at a given temperature. Just we have a relation to give us delta H. And that's why when we write down, when we need to calculate the enthalpy either for the product or the reactant, we equal to the summation of number of mole for each element in the product or in the reactant, multiplied by its enthalpy of formation plus delta H. Enthalpy of formation and delta H we can get actually from the table for any element, and we'll see inshallah how we can calculate. This enthalpy of formation, enthalpy of formation, in case of exothermic reaction, like this reaction of carbon dioxide, to formulate carbon dioxide as the reference point, it will result in heat. So it can be actually a negative sign in case of endothermic reaction. And it can be actually of positive sign in case actually, well, negative if it is exothermic, because the heat has a negative sign if it is leaving the system. So in case if we have exothermic reaction like the carbon dioxide, in this case, its sign should be negative in this case. You will see the value in the table is a negative value. Negative values, that mean actually this is an exothermic reaction. And it can be a positive value in case actually if we have endothermic reaction in this case. And the enthalpy of formation can be a value of 0 for actually the natural compound, natural gases that are actually existing under the atmospheric condition. Like if we have O2 or N2 or actually argon or hydrogen, H2, all of these gases under the reference temperature, we don't need actually to formulate them. Already at the reference standard atmospheric condition, O2 is already created. We don't need actually to have a reaction to create O2 or N2 or argon. So actually for the natural compound, in this case actually the enthalpy of formation to create them under the atmospheric condition is equal to 0 in this case. Okay? So is it clear, ya shabab?
Clear. Yeah.
So, Yazid, is it clear?
Yes, it is. Yes, it is.
Sorry. Have you have been in contact with this information before? The first law analysis for a reacting system? As a chemical engineering, have you been actually in contact with this? I think you should be.
Yes, but maybe not with it.
You have been in contact with, but not applied to internal combustion engine or combustion engine in general, maybe. Type anyway, Shabab. So let's summarize all of this. So the first law of thermodynamic will be Q minus 4 equal to H product minus H reactant, and this calculated in kilojoule actually per kilomole. And H product, when I calculated H product or H reactant, will equal to the summation of number of moles from I equal to 1 to N multiplied by enthalpy of formation plus delta H. Okay, enthalpy of formation and delta H, we can just get them actually from tables. Table A3. If you look there in table A3, you will find here in this table, we have table from A5 to A6. A1 will give actually the molecular weight, the specific heat at constant pressure, specific heat at constant volume, the gas constant for a list of substance. And here actually in table A3, you will find actually for each element like nitrogen N2, it will give you here the enthalpy of formation of nitrogen, which we said nitrogen is a natural gas under the reference point, so its enthalpy of formation is 0. Molecular weight is given, and here actually for a range of temperature you will find delta H is given, also actually the reference entropy is given in this case. Well, here actually the data for N2. Also here in this subtable you will find the data for N, and similarly you will find the data for O2, O, and all of other gases. In this case we can see delta H at a given temperature for range of temperature is given, and the value of the enthalpy of formation is also given for any species in this case. But if we have a شباب delta H, we need to calculate delta H, and the element is not listed actually in the list of element in table A3. Then in this case we can say delta H will equal to Cv multiplied by delta T in this case, which will equal to Cv multiplied by delta T, the temperature at which actually the element is existing, minus the reference temperature, which is 25 degrees C. But in this case, شباب, this temperature should be in degrees C. So if you will say delta T minus the reference temperature in degree C, that means this temperature should be in degrees C. If this one in Kelvin, that means this one should be in Kelvin in this case. And Cv شباب is a specific heat actually at constant pressure per kilomole of the fluid. This is calculated in kilojoule per kilomole Kelvin. But if you look at the data in table A1, based on which we can get the specific heat, the data here gives the specific heat in kilojoule per kilogram Kelvin. That means in this case, for this element, we have a specific heat per kilomole will equal to the specific heat per kilogram multiplied by the molecular weight in this case. If we are talking about carbon, nitrogen, carbon dioxide, water vapor in the combustion equation, and I need to calculate delta H, and the value is not listed in the table. So in this case, we can say delta H will equal to Cv multiplied by delta T. Cv per kilomole will equal to Cv in kilojoule per kilogram Kelvin multiplied by the molecular weight of this element. If we are talking about, let's say, H2O, water vapor, so it will equal to the value listed in table A1 multiplied by the molecular weight of water. Then we can calculate the specific heat per kilomole. Then we can multiply Cv by delta T, then we can calculate delta H. So the value of Cv and the molecular weight are calculated actually from table A1 in this case. Okay? Is that clear, شباب? So just I want to, and still we have some time, I will go through this. This is all what we said, but let's have this example to just to see how we can apply the first law of thermodynamic for a reacting system and how we can calculate the heat transfer or the work out of this system. Right here, in this example, he said we have propane fuel. So propane fuel in the liquid form. So you have to be careful about, because if the liquid form or the vapor form, the enthalpy of formation here, the value of the enthalpy of formation listed in the table, you will see actually it is different from if the fuel actually is existing in the liquid form or the gaseous form. Like say we have ethanol in this case, if it is in the gaseous form, that should be the value of the enthalpy of formation. If it is in the liquid form, that should be a different value for the enthalpy of formation. And the difference between them, ya shabab, is what? The enthalpy of formation to create actually a fuel under standard condition from its basic component. If it is in the liquid form or the vapor form, what should be the difference between the two enthalpy of formation? It should be what? The latent heat of vaporization. In order to convert the fluid from the liquid phase to the vapor phase, in this case we have to add amount of heat which equal to the latent heat of vaporization. The amount of heat required in order to vaporize this fuel from the liquid form to the vapor form. So when I say to you we have a propane fuel in the liquid form, liquid propane, so I will go back to the values here in the table. So the values here, propane, this is propane C3H8, this is in the gaseous form, and this is in the liquid form. In the liquid form, this is in this case actually this will be the value of the enthalpy of formation. But usually, this table for some different fuel, you will find those values of enthalpy of formation are listed in table, I think table A5. You can look here. So here it is, Shabab. Table A4. Yes, in table A4. You will find here for a list of substance. Here from table A4, list of fuels mainly. So usually if we are talking about element like NO, NO2, N2, O2, you will find the value of the Ensemble Formation is listed here. But if we are talking about fuel, so in this case the Ensemble Formation, we can get this value for different fuel. It is listed actually in table A4. So this is the molecular weight of the fuel, and the Ensemble Formation is given, and also the reference entropy is also given for a given fuel. So be careful if it is in the liquid form. In this case, the Ensemble Formation will be different in this case. Right, here we have, he said we have a combustion chamber, intracombustor. So we have liquid propane intracombustor. So in this case, we are talking about the combustor only. We are not talking about the engine. That means in this case, the work should equal to what, Shabab? Work should equal to 0 in this case, because I'm studying the combustor in this case. So we have liquid propane, C3H8. So this is in the liquid form, coming into this combustor at temperature equal to 25 degrees C. And he said actually the mass flow rate of this fuel, M dot fuel, is equal to 0.5 kilogram per minute in this case. This liquid propane is burned actually with 50% excess air. So air is coming with 50%. So lambda is equal to what, Ishbak? If we have 50%,
1.5.
exactly, so it will equal to 1.5 in this case. And he said actually this air is coming at temperature is equal to 7 degrees C. So the fuel is coming at temperature 25, and air actually is coming at temperature equal to 7 degrees C, which is actually 280 Kelvin in this case. They are burned together actually inside this combustor, and they resulted actually in combustion product. Those combustion product actually, he said, all of the hydrogen in the fuel will be converted actually to H2O, but he said actually the carbon in this case, 90% of the carbon is converted to carbon dioxide, and we have 10% of the carbon has been converted to carbon monoxide in this case. And they said all of the combustion products are existing at temperature 1500 Kelvin in this case. So this is the temperature of the combustion product. And we need to calculate in this case, first of all, he asked to calculate the amount of mass flow rate of air, and also we need to calculate actually the rate of heat transfer out of this combustor. So as we are studying this combustor, so in this case, we don't care about the engine, just we have hot exhaust gases in this case at 1500. If we took those exhaust gases and we pass it actually for a gas turbine, for a turbine, then in this case we can convert actually this heat, we can convert it to work in this case. But in this case, we are just studying this combustor. So in this case, for this combustor, we don't have actually work out in this case. But before proceed actually with the first law of thermodynamic, just we need to calculate the mass flow rate of air. So the first step to solute, for the solution in this case, I will just write down the combustion equation. So for 1 kilomole actually of C3H8 plus air, which is lambda 1.5 multiplied by gamma, which is x plus y over 4, which is 3 plus this over 4, so it will be 5 O2 plus 3.76 N2. That should give us what, Shabab? Give us 3 CO2, but he said actually 90% is converted to CO2. So it will be 0.9 multiplied by 3 CO2 plus 0.1 multiplied by 3 CO. And actually plus H2O will be N8 over 2, which will be 4 H2O, plus lambda minus 1, which is 0.5 by 5, so it will be 2.5 O2, plus 1.5 by 5, which is 7.5 multiplied by 3.76 N2. Is that clear, Shabab? This is for the combustion equation in this case. Right, can we calculate the air to fuel ratio? So the air to fuel ratio will equal to the mass flow rate of air divided by actually the mass flow rate of fuel. Mass of air is equal to what, Shabab? Number of moles 1.5 multiplied by 5 multiplied by the molecular weight multiplied by 28. This is divided by the mass of fuel, which is 3 by 12, 3 multiplied by 12 plus 8 by 1, and this should give us actually the actual air to fuel ratio. If you calculate this value, it will equal to 23.4 kilogram air per kilogram fuel. But he said actually here in this problem, he gave us the mass flow rate of fuel. So can we calculate the mass flow rate of air? So this is actually 0.05 kilogram per minute. We can leave it kilogram per minute. Then in this case, from this ratio, we can calculate actually the mass flow rate of air in this case. Okay. So we calculate the air to fuel ratio. I have to start with the combustion equation, calculate the air to fuel ratio. Mass flow rate of fuel is given in this case. Then we can calculate the mass flow rate of air. But what about the heat transfer? How we can calculate the heat transfer? So we have to apply the first law of thermodynamic for the reacting system in order to calculate the heat transfer in this case. But in this case, we are studying just the combustion chamber, so we don't have work. So Q minus work should equal to H product minus H react. In this case, we are studying the combustor. We don't consider the engine in this case. So in this case, the heat transfer will equal to H product minus H reactant. Type H reactant will equal to what? H reactant, we have 1 kilomole of the fuel plus this number of kilomole of oxygen plus nitrogen. So the enthalpy should equal to the number of moles for each element. So 1 of C3H8, the enthalpy of formation, then plus delta H for the fuel, which is C3H8 in the liquid form, plus 1.5 by 5, the enthalpy of formation, plus delta H for O2, plus 1.5 by 5 by 3.76, the enthalpy of formation, plus delta H for nitrogen in this case. And that should give us actually the enthalpy of the reactor. Let's look at the temperature. Fuel is coming at 25 degrees C. At 25 degrees C, the reference temperature is 25. So that means if the fuel is coming at 25, that means delta H should equal to what? Should equal to 0 in this case. And the enthalpy of formation for the natural component like O2 and also like Na2, their enthalpy of formation actually is equal to 0. So we need to calculate the enthalpy of formation of liquid propane. We need to calculate delta H for O2 and the Na2. This is coming at temperature of 7 degrees C, which is 280 Kelvin. We need to calculate delta H at this temperature, and also nitrogen is coming at temperature of 280 Kelvin in this case. So if I go to table A3, then I can go for oxygen and nitrogen, and also from table A4, I can get actually the enthalpy of formation of liquid propane. Okay, the enthalpy of formation of liquid propane, if you went to the table, this will be the enthalpy of formation of liquid propane, which is 118 actually 910. This is actually in kilojoule per kilomole. This is the enthalpy of formation of the fuel, which is liquid propane. This is the value in this case. But for oxygen and the nitrogen, the enthalpy of formation is equal to 0 in this case. This is for the reactor. Okay. But what about delta H? Delta H for O2 and delta H actually for nitrogen. We can just go to table A3. So here is table A3. You can search actually for O2. The table for O2. This is CO2. This is O2. At a given temperature, shabab, which is 280, you will find it between 200 and 295. So in this case, you have to make interpolation between the two values. Then we can calculate the value of delta H in this case. If you calculate the value of delta H for O2, unlike this for N2, at 7 degrees C or 280 Kelvin, then in this case, we can calculate the value of delta H. I prefer to use this table. Then we can just substitute here, then we can calculate the enthalpy of the reactant in this case. So what about the enthalpy of the product? The product in this case will be actually, we'll have CO2, CO, H2O, N2 and O2 in this case. And it will be the similar way. We can just get the value from the tables, and then you can just look at, you can just substitute in the equation. So the enthalpy of the product will equal to, the product we have 0.9 by 3 CO2. So multiplied by enthalpy of formation, that plus delta H for CO2, plus 0.1 by 0.3, 0.1 by 3, this is CO, so the enthalpy of formation plus delta H for CO, plus 4H2O, so 4 multiplied by enthalpy of formation plus delta H for H2O. Just I will add the whole component issue, unlike this actually for O2 and N2. The product in this case are leaving at temperature 1500 Kelvin. So in this case I will go for the table for CO2. From table A3 I will calculate delta H at this temperature and get the value for delta H for CO and delta H for H2O. Unlike this actually we have also in the product we have O2 and we have N2. So we get the value of delta H. For the product, for CO2 also, from the same table, I can get the value of the ensemble of formation. For CO from the same table, table A3, I can get actually all of these values. Then I can calculate actually the ensemble of the product, kilojoule per kilomole in this case. Fine. In this case, we can just substitute and we can say the heat transfer will equal to actually the difference between the enthalpy of the product and the enthalpy of the reactant. It will be calculated in kilojoule per kilomole. But he asked it to calculate the rate of heat transfer or the power actually of this engine. So this is the heat transfer per kilomole fuel because we have written the combustion equation per kilomole fuel. So in this case, if I divided by this heat transfer, if I divided actually by the molecular weight of the fuel. Molecular weight is kilogram per kilomole. Then in this case, if I divided this value by the molecular weight of the fuel, which is C3H8, C336 plus 8, so it will equal to 44 kilogram per kilomole. So if I divided by the molecular weight of the fuel, in this case we can calculate the total heat transfer. It will be calculated in this case in kilojoule per kilogram fuel. But I need to calculate the power. Power, that means the rate of heat transfer. Rate of heat transfer will equal to the mass flow rate of fuel multiplied by the total heat transfer. This total heat is kilojoule per kilogram, and the mass flow rate of fuel is in kilogram per second. So kilogram will go with kilogram, it will be kilojoule per second, which will be in kilowatt in this case. So the value that we calculate H product minus H reactant will be in kilojoule per kilomole fuel, because we have write down the combustion equation per kilomole fuel. If I divide it by the molecular weight in kilojoule per kilogram per kilomole, I can get the total heat transfer in kilojoule per kilogram fuel. Then if I multiply it by the mass flow rate of fuel, then in this case I can calculate the power of the reactor in kilowatt. Is that clear, Shabab? Clear, Shabab?